to the web server as these table attributes, female and race. That's not the information I want, though, so having already mined the system catalog, I know that ID and password are valid fields. Let's just hope that they're not checking very carefully on the web server side that I'm not trying to pull out those attributes. Sure enough, there's no error checking that's going on. Now I've gotten a dump. It scrolls way off the bottom of the page. I've got every single user and every single password from the entire system in one query. So hopefully I've convinced you that these database systems, there's a reason to protect them, that the threats that can go on are pretty severe. I focused there just on SQL injection. This is a list of the top 10 database threats that was put together by the Imperva Corporation. We want to do more than just stop SQL injection, though. There are people who are legitimate insiders who have been given more privileges than they strictly need to fill their role. We want to prevent them abusing those excessive privileges. There are people like admins who have a lot of privileges and need them for a very good reason, but they still might abuse those privileges. We want to stop that sort of activity. We want to stop people elevating the privileges that they were given to be able to masquerade as somebody with higher privileges. I put OS vulnerabilities with an asterisk because it is our contention, and we'll test it with a red team exercise, that if there are holes in the OS, but you want to get information out of the database, the easiest way is still to go through the SQL engine and not try to pull the bits off of disk and reconstruct it elsewhere. And then there are other liabilities to the system, such as vulnerabilities in the protocol that the applications communicate back to the database through, or if people have crummy passwords, then somebody from the outside might be able to masquerade as an insider. Things we're not tackling that are still important, having audit trails. We actually rely on the audit trails in order to do the anomaly detection. We got nothing to say about denial of service, and if your backups are somewhere where somebody can steal them, that's entirely out of scope as well. So that's what's the big deal, why I think that defending these database systems is an important thing to do. Next, I'll look at the architecture of the database engine and describe where it is we're going to start doing our monitoring before talking about exactly how we do the monitoring. So here is a picture of a database stack. At the top you have the applications or the SQL interfaces that are running on the database. The SQL commands get fed into a query parser. The result of that is passed off to a query optimizer that rearranges terms inside the query so that you can push your selects down so that you're throwing away unnecessary data as quickly as possible, etc. All sorts of things happen inside the plan generator and the plan cost estimator. Then the query plan is handed off to an evaluation code, and that needs to go through and deal with managing transactions, figuring out how to get the data off of the file system, maintaining the main memory buffers, etc. In terms of related work, most of the focus so far has been on the layer of SQL commands. So for the database activity monitoring vendors that are out there, they really tend to focus on looking at SQL commands. Some work that came here out of CERIAS also looked at SQL commands. I'd say about half of the academic work focuses on the SQL commands. It's attractive because it sits entirely outside the database. It's really easy to get your hooks into. But I'm going to argue that we can get more information from deeper levels of the database system. But first, other places that people have looked. One interesting place to look is inside the transaction manager. Once you're down at that level, you know what the sequence of reads and writes has been. That's a lot of information at your disposal. The drawback is twofold. First off, you can only do your monitoring after the query has run because you have to observe the reads and writes, and by then it's too late to stop the attack happening. The second limitation of the transaction manager is because it's looking at the interaction of reads and writes, if there are no writes, it can't stop it. So attempts for exfiltration are not going to work very well at the transaction manager. There's been a little bit of work on looking at the system catalog. This helps you detect privilege abuses, but not much else. And then there's been some work on file access methods. This is very similar to other attempts to stop insider threats because you're monitoring the file system. But again, you can only do it after the fact. You can do it for detection or forensics, but you can't do it for actual prevention. So where instead we plug in is between the query optimizer and the query plan evaluator. And the reason for doing so is by the time the database engine has gone through the task of optimization, it's created a lot of useful information. At that point, you have good guesses about how big the result's going to be, how expensive it's going to be to compute that result, and you also have all of the information about specifically what tasks are going to be done in what order. And that's great information from the perspective of building up profiles of legitimate activity. So what features are we explicitly pulling out of the query optimizer? So the first thing we can get is we get an estimate of how much data is going to be read from each table. It's going to depend on the exact query. It's dependent on the statistics that are being maintained. So it's just a guess, but it's usually a pretty good guess. We get an estimate of the number of records that are going to be returned by the final query. We know exactly which access plan is going to be used for each table. Are we going to just do an exhaustive scan of the entire table, or are we going to use some sort of index to look up just the values that we're interested in? I won't go through all of the rest of them, but there is a myriad of other features, which attributes are being returned, what algorithm is being chosen to do any joins that are being performed, which user or role is purported to be being used, etc. To tie this back to some of the related work coming here out of CERIAS, related work by Camera and Bertino and one other name that I've forgotten. My apologies if that person is here. What they were looking at was what's being returned in the output, does it appear in the selection predicate, and what is the role. So they're looking at that subset that you can get out at the SQL command level before it's gone through the query optimization. So then, now that we know where we're plugging in and what sort of information, how do we detect anomalous behavior? First, sort of a side trek, if you will. Marcus Raynham has a blog that he rants in every once in a while. And one of the things he's put together is the 6 dumbest ideas in computer security. And he says that one of the dumbest things you can do is enumerate badness. And he uses this graphic to justify that. He says, look, by this point in time, the illegitimate activity exceeds the legitimate activity, and the illegitimate stuff just keeps growing. It's foolish to try to track all of the possible things that might go wrong when there's only a handful of things that you know are right. So instead, enumerate the stuff that you know is right, and everything else then by definition is at the very least suspicious. And so that's a tack that we've taken to heart. We're just going to enumerate the goodness and flag everything else as suspect. The technique that we're going to use is called cross-feature analysis. We kind of backed ourselves into a corner when it came time for building our profiles. When I talked about what was in the query optimizer and the sort of information we could get back out, there were things in there that were just straight numbers. Things like how many records we're going to return, how long it's going to take the query processor. For those sorts of methods, it's easy to compute a distance so that you can decide how far you are away from where you expected to be in some high-dimensional space. But once you start talking about things like, am I going to do a hash join or a sort merge join? I can't tell you if that corresponds to a difference in 50 tuples, 175 tuples. There's no good distance metric, so we had to scrap any technique that relied on distance metric. Similarly, we only have legitimate examples. We're only profiling the goodness, so we have to use only those techniques that allow us to build our profiles up only on known good behavior, a single class algorithms, these are called, of which there's only a handful. And once we put those two constraints together, the only thing we were able to find was this technique called cross-feature analysis. The way this works is, during the profiling step, you accumulate all of your historical data. You go looking through query logs or through performance tests. You then extract those features from the query optimizer, and then you build a decision tree for each of the features based on all of the other remaining features. So if we have 100 features that we're extracting, we build 100 decision trees. Each one predicts one feature based on the other 99. And the idea is that if in fact there are strong patterns, then knowing 99 of the features, you get a really good guess of what that last one is going to be. Then at decision time, at runtime, when a new query comes in, we extract the features just like we did before, but this time we're going to predict them using all of the remaining features and the decision trees that were built, and then we can classify as normal or suspicious based on how many we were able to get right. So let me walk through some examples of how this works, not using query optimizer output, but something that's a little bit easier on the eyes. We're looking at shapes, numbers, and colors. So those are going to be the sorts of features that we're looking at. And at runtime, we need to classify this red square with a 0, as well as these other two squares. And give you a moment to stare at those and decide for yourselves which ones you think look as legitimate and which ones look anomalous. So the first step now, we need to extract the features. So in this case, the features are pretty simple. For the first shape, we extract that it's a square, it's red, and the number is 0. And we similarly, for each one of our examples that we see, we extract all of the features. In our system, actually, this is being done from the query optimizer, but for this example, we'll use these features. We then construct models for each of the features. So the first one we'll construct is the shape feature. So across the bottom is the thing we're trying to predict, that's shape. And the decision tree says if you observe these things, this is